So let us continue our discussion with graphs. And for graph also, we have to talk about this abstract data type graph. Because we need to implement this graph, we have to think about this ADT, that is the information that is stored internally, as well as the functions which are going to interact with this data. We will store the data, or will store internally the graph in the form of nodes and the edges. And we will associate in both the cases data with node and edges. For nodes and for edges, for nodes, this could be some information on a user of social network, or a computer in a network, or say an intersection on a roadmap. While on edges, this may be the length or direction of a road, or amount of money one bank owes another, likewise. So when such data becomes more relevant later, we will return to them. But for now, we'll just concentrate on basic graph structure, and we'll try to keep in mind that we would often want to store more information at nodes as well as edges. So talking about this ADT for graph, the functions which should be there are adding and deleting of node, adding and deleting an edge, testing whether a specific edge, for example from U to V, exists, and for a node, say U, listing of all its incoming and outgoing edges or all adjacent edges. Means if this is, or these are nodes and these are various edges, then the information about these nodes and edges, and how to delete, add, test whether this specific edge exists or not, and etc. So the later part, this latter one, they are specifically used in the context of finding path between nodes. This is a very challenging topic, and very advanced solutions are there with the help of graph. A good iteration of this could be using iterators, that is, the function returns an iterator that will eventually output all the outgoing edges. And by using this iterator implementation, we can continue to hide from other classes how to this ADT stores information about the graph internally, and we will be only revealing the minimum information that is required. So how we are going to implement this ADT for graph? There are two natural ways to store a graph internally, and in both these cases, these two ways, we would store nodes themselves in an array, or perhaps a linked list or list or a set. Again, we would store nodes in an array, linked list or list or a set. So what are these two natural ways? One is adjacency list, the other is adjacency matrix. This adjacency list, for each node we store a list of all other nodes it is adjacent to. That is why it is adjacency list. And this could be used or employed or implemented using ADT set, list, linked list, or dynamically growing array. If the graph is directed, we would store two separate lists, because directed means we have to have a two separate list, one for outgoing edges and another for incoming edge ones. So the element of the list would be either pointers to other nodes, or if nodes themselves are stored in an array integers, that is the indices in the array where the other nodes are stored. So using this adjacency matrix, we store a n by n matrix, that is a two-dimensional array. You have n by n matrix, something like this. Say it is A, and in position A, U, V, we store whether there is an edge from U to V. Say this is U, this is V, and this could be a boolean value or perhaps an integer storing the length, cost, or any other information. What we store in position this A, U, U means same position, say this position. It depends on what our graph is modeling. In certain cases, it makes sense to treat it as though there were an edge from U2 itself, means like this itself. Okay. But in other cases, it may not be worth keeping it. So there is no rule that forces us to choose one or another, and we should use whatever makes our computational task, which is assigned to us, easier. Now, if we were to compare the two approaches, we should always look into account which operations we expect to be performed more frequently. This is very important. Let us compare these operations that are more or less expensive in these two type of implementation, namely adjacency list and adjacency matrix. For adding and removing nodes, an adjacency matrix has a bit of overhead more. Why? Because changing the size of matrix involves a bunch of reallocation and copying. In this second one we are talking. And for many applications that we want to solve, changes in the set of node tend to be a bit rarer while other processing is happening. And testing whether this edge from one to second node exists in the graph is the specialty of adjacency matrices. So it only involves one lookup in a known position if you have a two-dimensional array, and that will only take an order of one time. But on the other hand, adjacency list, we don't have that information readily available. Instead, it's a list, so we need to go through the list of all outgoing edges of U and see if V is in the list. And this will take at least this theta out degree U time, which can be much larger. And listing all outgoing and incoming edges, because they are separate list of U, is the specialty of adjacency list. And since they explicitly store this information, they just have to go through their set or list, whichever way we implement, which takes time of theta out degree or theta in degree. And for an matrix like adjacency matrix, we don't have this information stored. So we have to loop through the entire row or column of the node U and find all the entries that are 1 or true, or the number which we just discussed. This will take theta n times, which can be much worse if the degrees are pretty small. We can also compare the memory requirements of these two, adjacency list and matrix. For adjacency matrix, we need to store n by n array, which obviously requires order of n square. For list, we store all incoming and outgoing edges, which gives us a total memory requirement of theta in order plus out order, and PV are the numbers. So to evaluate this sum, we must notice that when we sum all in degrees, we count each edge exactly once, since it contributes 1 to the in degree of exactly one node. So the sum of all in degrees, this in degrees is m. Similarly, for sum of all out degrees, that will be say m. So it will be 2m. So order will be m. The total storage requirement will be around this m only, since n plus m will be for greater cases it will be n plus n or m plus m. So that will be 2n or 2m. For sparse graphs, adjacency lists are much more economical with space than this adjacency matrices. Whereas if we talk about this dense graph, it doesn't really matter too much in terms of memory. And we have seen above that each way of storing a graph has its own advantages and disadvantages. If memory is not a concern, one possible approach is to store the entire graph twice internally. When a user queries whether an edge exists, we answer it by using the adjacency matrix. While when the user tries to ask all neighbors or neighborhood of node U, we use list. So we can use a list and a matrix together also. But the downside is, of course, we have twice the memory. It requires us to execute each update to the graph twice, once in this matrix and once in the list. And this update operation, like adding, removing edges, that is going to take twice as long as before. But this may well be worth it for many graphs. Updates are quite less than the queries. Queries are more prominent. Just take an example when building a GPS. It is much rarer to have roads or intersection added to a road network than to load or look for routes between these two locations. Right? These are the examples. Uh, for us, this idea of doing more pre-processing during update time to speed up the later operation at query time is actually very important and active direction of data structures. And various research papers are trying to find useful internal representation of answer queries about this connectivity or shorter routing, which is quicker than with the default representation as we have discussed. Then coming to our graph search, BFS and DFS. So one of the most asked question about graphs is is there a path from U to V? What is the shortest path from U to V? What is the distance from U to every other graph in the every other node in the graph? So all these kind of questions and problems fall under the broad area which is graph search or computation of shortest path. These problems have many important applications like finding fast or cheap ways to go from one place to another, utilizing road networks or airline or traffic train networks. That is, we want to optimize the time and cost. For example, we have an example called Kevin Bacon game, in which these players try to construct a short sequence of movies that connect a given actor to an actress. To the actor Kevin Bacon, you know about Kevin Bacon. There is an edge between two actors if and they co-starred in at least one movie. And there are various examples. So graph search algorithms are one of the most central concept of for computer people to be familiar with. And as we just now briefly mentioned above, there are a few parameters along which we concurrent instances can differ. For example, do we just want to know whether a path exists or we need to find it? If we need to find a path, do we want to have a shortest path or will any path do? And if we don't need to find it, do we need to exact distance between nodes or just whether the path between the two points exists? And do edges have length, cost associated with them, or we just concerned with the number of hops? Or rather, edges have costs associated with them, and can they be negative? So all these questions turn out quite general. The problem doesn't get much easier by just asking whether a path exists. So the algorithm we will be investigating will actually find a path, and the most natural algorithm, that is BFS, actually find a shortest path. On the other hand, edges length, cost make the problem a bit more challenging, but we'll see how to deal with them. So we'll cover rest of this later. Thank you so much.